Hi guys, welcome to our first lesson, which is the first lesson of chapter 5. Some of the questions that we're going to be answering today are what is a radian, what does it measure, and what's its relationship to a circle? So first of all, you should actually know this from last year, but see if you can take a second and recall what a radian was. And maybe it might help you to talk about what it measures and then what's its relationship to a circle. And if you want to pause the video so you can think, go for it. Okay, so a radian is really a way that we measure angles. So in your calculator, you'll notice that you have like degree mode and radian mode, right? And so we can switch back and forth. They both measure angles, but the nice thing about radians is that they do have this relationship to a circle. So that's what we're going to talk about. So let's dig in a little bit more. Okay, so we know there's 360 degrees in a circle. We'll start basic. And we also know the circumference of a circle is 2 pi r. So that's really important. So we know that the distance around a circle is 2 pi r, and we know that there are 360 degrees in a circle. Okay. Okay, so we wanted a nice way as mathematicians to relate angles to the size of the circle, right? So that it just wasn't an arbitrary value like degrees are. Okay, so what we did is we basically said, if we have an angle, like check out this angle here that I have drawn on my circle, right? So this angle measure, if I made sure that I opened it up so that this angle opened up the same width, so that this length, like if I literally took a string and measured from A to C, that length would be the same as the radius of the circle. So we said, okay, well, if we open up to the radius length of the circle, let's call that 1 radian. Meaning it's basically, I have to open up enough on this arc so that it's the same as the length of the radius. So now that angle is a radian. So what if I have different sized circles, right? Which I have here on my picture. For example, see this little circle, this middle circle here? It's opening the same angle. We can tell because the angle didn't move, right? I didn't magically change the angle on you while you guys were looking away. So this angle is the same angle. And my arc, you'll notice, is smaller. In fact, it's smaller at the same ratio that the radius is smaller. So this radius length, BG, is equal to this arc. So when I shrink my circle, that doesn't change the relationship. If this is open to 1 radian, then that means it's opening 1 radius length, right? So IG, this length of IG, which I think I have maybe here. Yeah, this length is still the same as this radius, okay? So this is 1 radian. Okay, so again, we noted that it doesn't make a difference how large or how small your circle is, right? The angle that's 1 radian creates the same angle, okay? So again, you want to think of radians as being equal to an angle that opens up 1 radius length. We're going to do a lot with moving around the edge of a circle, traveling. And so if you can remember that 1 radian is just an angle that opens up 1 radius length, that will be very helpful. Okay. So if I were to give you this value, I can tell you that 1 radian is about 57.3 degrees, right? So that's pretty abstract, right? I mean, that it doesn't match up nicely, but let's talk about some ones that might match up nicely. So what if I asked you how many radians would be in a whole circle? Okay, so let's dive into that a little bit, but let's do it by making it a little easier. So let's think about a circle with a radius of 1. And we call this the unit circle. You might remember that, again, because it's 1 unit wide. We're going to use that a lot this year. It's got the center at the origin, and it goes out to 1 in each direction. Okay, so what is the circumference of this circle? Right, it would just be 2 pi. Because if your radius is 1, my circumference would be 2 pi. Okay, so how many radians of angle measure are there if you go all the way around the circle? Remember, guys, if I'm asking you for radians, I'm asking you how many radii, right, would fit around the circle. Well, this literally tells you, it said it would give you 2 pi radii. So it's 2 pi times the length of the radius. So it's literally saying you have 2 pi radius lengths around that outer circumference. And most of you had this last year, so you know that. So that means that 360 degrees all the way around the circle is the same as 2 pi. So we can figure out some of our nice angles that we end up using a lot just by looking at proportions. So let's try some of those out. Again, you should have done these last year. Okay, if I have an angle that is 0 degrees, which doesn't open at all, then that would be 0 radius length, right? That's easy. And I'll throw the 360 back down here. 360 we said was 2 pi. So let's think of an easy one that we could get. Well, let's go up to 180. 180 is how much of a circle? Half. So then it should also have the same value for radians proportionally. So half of 2 pi, pi. I guess we could do 90 as well, right? So if I do 90, 90 would be half of 180. And so that would be half of pi, or we say pi over 2. All right, let's get some of these nice easy ones. If I wanted to go from 90 to 30, I would have to divide by 3. So that would be pi over 2 divided by 3 would be pi over 6. 45 is how much of 90? Half. So that would be half of pi over 2. So half of pi over 2 is pi over 4. And then if you wanted to get 60, what I would actually do is start with the smaller guy. So like 30 goes into 60. 30 times 2 would give you 60. So then I could take pi over 6 times 2, which is pi over 3. So then this guy's pi over 3. So why don't you take a second, pause the video, and see if you can fill in the rest of these. Okay, so you should have paused the video. Now we're ready to look at the answers for these last few ones. So let's fill those in together. I did 120 by taking, you could do 60 times 2. That would be 2 pi over 3. You could also have done 30 times 4, but you would have had 4 pi over 6, which you, of course, should reduce. We will always reduce in this class to 2 pi over 3. Anything that ends in a 5 is always a multiple of 45 for our chart. So this is 45 times 3. So this guy was 3 pi over 4. 150, 30 times 5, so 5 pi over 6. 210, I think I did 30 times 7. So then that would be 7 pi over 6. 225 ended up being 45 times 5, so 5 pi over 4. 240, I did 60 times 4, so that gave me 4 pi over 3. 270 was easy. That's a multiple of 90. 90 times 3, so 3 pi over 2. 300, I think I did 60 times 5, so that was 5 pi over 3. 315 was 45 times 7, so 7 pi over 4. And then 330 was 30 times 11, so 11 pi over 6. Some of those larger ones gets a little trickier, but so these are the ones around the unit circle that you are probably familiar with from last year. We're going to use these a lot, so you're going to want to kind of start knowing these synonymously with each other. But if you forget, again, you can kind of like if you're like, oh my gosh, what was 210? Well, 210 is a multiple of 30. It's 30 times 7, so it's 7 pi over 6, right? So if you know these guys here, you could probably get everybody else. All right. So what about angles that aren't special, right? Because maybe not all of them are these special like 30, 60, 90, 45 angles that we used a lot in geometry and so on. What if I have something different like 216 degrees and I want the radians, right? Or how many degrees are there in 17 pi over 2 radians? What if I want to go back to degrees? You know, how can we go back and forth? So what do you suppose we could use to represent in terms of the angle measure? So how could we find that? Well, what we noticed here is that we used a lot of ratios, didn't we? So we used like, oh, we know, that there's 360 degrees for every 2 pi radians, right? So like if you were trying to figure out how much there was in 180, we just set up this kind of proportion or ratio, right? And so we said like, oh, if I divide that by 2, I divide that by 2. And then I can keep solving these proportions. Okay, so we can use any proportion to help us solve this. The easiest proportion, if I look back at my chart, 360 and 2 pi are nice, obviously, degree to radian relationship. These all get kind of messy because they all have fractions. So I would pick something nice. Do you guys see a nice relationship between degrees and radians? Yeah, I would pick the 180 to pi because it's a nice, they're both nice values. There's no fractions involved. 360 and 2 pi isn't bad, except you could reduce them both by 2. So that's why we're going to use 180 over pi. So this is the relationship that we're going to use, 180 degrees for every pi radians. Oops. So let's actually, I'll stay on this same page. Let's do it. Let's convert some of these. So how would that look like if we wanted to convert? So let's do the one that's 216 degrees. So if I wanted to convert 216 degrees, this is where notation is really helpful. 216 degrees, if I want to convert to radians, check it out. You're going to want to multiply by your relationship, but you're going to need radians on top and degrees on bottom. The reason you'll need it that way is because then the degrees will cancel and you'll be left in radians. So what's our relationship? We know that there are pi radians for every 180 degrees. And so then I can reduce that fraction, which is I'm doing right now in my calculator. So I'm putting in 216 over 180, and then I'm hitting my math to frac button. And let's see, maybe you guys aren't familiar with that. So let me pop out my graphing calculator real quick, and I will show you that. Okay, so what I'm doing is I'm just putting in, must have opened two of them. Okay, I'm putting in the 216 over, which is just the division symbol. Oops, doesn't want to do it on my keyboard. Okay, 180. Okay, so then I'm hitting enter. And then when I get that decimal, I can go to the math button here. And then that first choice is to fraction, and it'll change it to a fraction in lowest terms. So if you didn't know that, now you do. Okay, so it's 6/5. So I have 6 pi over 5. So there I am in radians. Cool. So there's a quick conversion. What if I wanted to go the other way? The other one we had was 17 pi over 12. Now remember, this is in radians. So if I want to multiply and be in degrees and cancel out radians, I need the radians on bottom to cancel. So then I'm going to have the 180 on top and the radian of pi on the bottom. So see the difference? Okay, depends what you want to end up in. The radians are going to cancel, which means I'll end up in degrees. Okay, so then I'm going to do 17. Well, you can see here the pi's are going to cancel, so that's nice. So now I'm going to do 17 times 180, which was what was on the top. And then I'm going to divide by 12. Oops, I did 13, didn't I? Let's try that again. So 255. So I end up with 255 degrees. Okay? All right. Okay, so let's take a look forward. Let's just review. We're going to use these special right relationships a lot. So I just want to review these so you guys can have these in your memory from last year. So special right triangles, we have 45, 45, 90 triangles, and we have 30, 60, 90 triangles. Okay, so let's see what you remember. In a 45, 45, 90 triangle, well, these two sides are the same. So if I let this side be, x, that means this side is x. Does anybody remember what the hypotenuse is? It's a relationship on x. It's x root 2, right? So whatever this side is times root 2. And if you want to go backwards, you would just divide by root 2. So like if this side was 5, then the hypotenuse would be 5 root 2. If this side was 8 root 3, whoa, I'd still multiply by root 2. 8 root 3 times root 2 would give me 8 root 6. Okay, and then a 30, 60, 90. So first of all, you get a 30, 60, 90 triangle by taking an equilateral triangle and dropping that altitude. So it split that angle. In an equilateral, they're all 60 to begin with. So then I split that, and so it splits this side in half. So this side right here is half as long as that side. Okay, so whatever this side is, we have x. This side is always double that, and this side is x root 3. Okay, so that's pretty easy, right? All right, but let's get this useful for our purposes. In our purposes, we're going to want the hypotenuse to be 1. So because we're going to use the unit circle. So I'm going to make the hypotenuse of all these triangles 1. Okay? If that's the case, knowing what I just said, if this side is the leg times root 2, then to go backwards, we have to divide by root 2. So if you remember 1 over root 2, you have to rationalize it, comes out to root 2 on top and 2 on the bottom. So in a 45, 45, 90, if the hypotenuse is 1, each of the legs ends up being root 2 over 2. Hopefully you remember that. All right, in a 30, 60, 90, if the hypotenuse is 1, remember the short side, which is across from 30, the short side is always half the side. So half of 1 is just 1/2. And then I have to multiply this side by root 3 to get the long leg. So the long leg is root 3 over 2. And then this is a 30, 60, 90 just drawn in a different direction. So if the hypotenuse is 1, remember short leg across from 30 is 1/2, and long leg is root 3 over 2. So these are the sides you really need to know. We always want to know it when the hypotenuse is 1, and then we can make it bigger if we want to, but it's easiest if you start with that. So that's where I'm going to go. Okay. So I just want to look at our unit circle a little bit with some of these special right triangles. So check this out. So this first triangle that I've drawn here, I've drawn at a pi over 4 angle. And whenever we do these angles, we typically start kind of like from that, we call this like 0 degrees or 0 radians, and we go this way. Okay, so I went pi over 4. How much is pi over 4? 45 degrees, right? So this is a 45-degree angle, but we're going to start calling it pi over 4. Okay, so then what are my two sides? Well, again, if this is a unit circle, this is 1, which means both of these are root 2 over 2. And that means that the coordinates out here, this point right there, that's important to note. That point, which is on the unit circle, that's why this is 1, right? That point has coordinates. Look, your x direction, you want a length of root 2 over 2. And your y direction, you want a length of also root 2 over 2. So there's your coordinates to get you to that point. Okay, so let's do the same thing. Let's take this same triangle, but put it over here in the second quadrant. So does anything about the triangle side lengths change if I flip it over here? I hope you said no. Nothing about the side lengths changed. I literally just reflected it. So this side's still root 2 over 2, and this side's still root 2 over 2, and that side's still 1. But one thing did change, right? Which coordinate changes? The x-coordinate, because I'm on the negative side of the x-axis. So everything about your coordinates stays the same, except you just have to change the sign. Now, to not confuse people with sign, S-I-N-E, we talk about this as being the parity. So if you want to talk about whether a number is positive or negative, we talk about its parity. So like the parity changes, so this becomes a negative. Okay, if I flip that same triangle down here into the third quadrant, same thing, but they're both negative, right? And then down over here, I'd have a positive x value and a negative y value. Okay. I can do the same thing with like a pi over 3. How much is pi over 3 again? If you forget, remember, you can think of it like this. Pi is 180. So pi over 3 would be 180 over 3. So 60, again, if you're trying to remember. So this is a 60-degree angle. So that's a 60, 30, 90. Hypotenuse is 1. Remember, the short side is 1/2. The long side is root 3 over 2. So there are your coordinates. When I flip it over here, I have a negative x and a positive y, but the coordinates are the same. Same things as you move forward. Now, I want to show you something that you're keeping in mind as we're looking at this. If I want to talk about this point, right, which we already know the coordinates, we talked about them. This little angle right here is pi over 3. So how much is this angle? Well, it would be 180 minus this little angle, which most of you know is 60, so it's 120, or you could think of it as, if that whole thing is pi, it would be pi minus pi over 3, so this angle is 2 pi over 3. So we're going to refer to this set of coordinates as being like a 2 pi over 3 angles coordinates, right? Because the pi over 3 is only really referring to the angle inside the triangle. We call this little triangle a reference triangle because it's a pi over 3 reference triangle, but the actual full angle is 2 pi over 3. Okay. We'll do more of this in class. And then same thing here, I just did a pi over 6. Remember, if pi is 180, pi over 6 would be how much? 30. So this is really a 30-degree angle. So this is a 30, 60, 90. So the short side's 1/2, which is now the y value. And the long side is root over 2, the x value. And then again, depending on where I move that reference triangle, I'm changing the parity of those coordinates. I just want to point out also, these little reference triangles, I'm always giving you the little angle measured from the x-axis, right? So we're never measuring it from the y. We're always measuring it from the x-axis. Okay, that's the first one. First video, we're going to talk about this a little bit in class. In fact, I might actually do this stuff in class, this first one, and then we'll go from there. Okay, I'll see you guys soon.